Now we'll discuss about eigenspaces and two multiplicities. One is geometric multiplicity and algebraic multiplicity. Okay, let's first see what an eigenspace is. Let A be a square matrix C n cross n, and for a given lambda, which belongs to the spectrum of A, the set of all x's which belong to C n, set of all x which belongs to C n, such that A into x is equal to lambda x is called the eigenspace of A, corresponding to a particular lambda. So eigenspace of a matrix is actually denoted by eigenspace of lambda. So it is the set of all x's in C n cross n which satisfies Ax is equal to lambda x. So every x in the eigenspace of lambda is an eigenvector corresponding to a lambda. So for a particular lambda, we have not just one eigenvector, we have multiple eigenvectors. One way of obtaining the eigenvector is actually to multiple eigenvectors is to scale the eigenvector which we have, one basic eigenvector we have. So for example, x is an eigenvector, c is also an eigenvector. Okay, so that is the eigenspace corresponding to lambda. Or another way of defining eigenspace of lambda is it's a set of all solutions to the equation a minus lambda x is equal to 0, or it is a set of all solutions. It's actually eigenspace of lambda is the null space of a minus lambda I. So it is a subspace. Null space of a minus lambda I is actually the eigenspace of lambda. Null space of a minus lambda. Okay, I hope so. There are two definitions which I've already told. One is the set of all x's belonging to Cn, which satisfies the equation Ax is equal to lambda x. Another way to say that is it is a null space of a minus lambda into a, eigenspace of lambda. Okay, using this, we can actually, using eigenspaces, we can actually define another multiplicity. So you've already seen what is geometric multiplicity. So even though there's a more systematic way of defining geometric multiplicity in terms of derivatives, the simple way is it's the number of times the lambda repeats as a root in the characteristic polynomial of A, is the algebraic multiplicity of a matrix A. Now, if you want to find geometric multiplicity, sorry, it's the algebraic multiplicity of not a matrix A, of an eigenvector. Now, if you want to find geometric multiplicity, it is actually the dimension of the eigenspace corresponding to lambda, or it's the dimension of the null space of A minus lambda I. It's the geometric multiplicity. So typically, geometric multiplicity is less than or equal to the algebraic multiplicity of lambda. So using this, the geometric multiplicity and the algebraic multiplicity, we can define defective and non-defective matrices. So if a matrix, so we've already seen the geometric multiplicity can be less than or equal to algebraic multiplicity. If the geometric multiplicity of lambda is less than the algebraic multiplicity of lambda, then A is called a defective matrix. And if they are equal, geometric multiplicity of lambda is equal to algebraic multiplicity of lambda. For all, so that is also important, not just for one lambda, for all the lambdas belonging to the spectra of A, then the matrix is called a non-defective matrix. And a matrix is non-defective if and only if it's if and only if it's diagonalizable, or the vice versa. If the matrix is diagonalizable, it has to if and only if it's non-defective. So all these properties which we have already seen for diagonalizable matrices will also extend to the non-defective matrices, which has the geometric multiplicity equal to the algebraic multiplicity. Okay, these are about eigenspaces, algebraic multiplicity, and geometric multiplicity.